Alright, my friends, in this video we're gonna look at, as a math review, really related to our course, scalars and vector quantities. A very major confusion is vector quantities, so I want you to get on board, get some understanding. We'll keep going back to vectors and how to deal with them, and hopefully you guys will be expert by the end of this course. So we have two types of quantities, simply scalar and vector quantities. If I have a scalar quantity, it can be described with a single number, like a kilogram of apples, 50 liters of water. When I tell you that, you have all the understanding, no confusions there. That's a scalar quantity. Vectors cannot be described only by a number. They need a strength, a length, and the direction. For example, if I tell you I am driving at 60 miles per hour, you would have questions. Where are you going? You tell me, right? Or which direction are you driving, and so on. So this is an example of vector quantity. Quantity velocity is a vector. I have to tell you the direction. So it needs a magnitude and a direction. I am driving 60 miles per hour to east. As we discussed earlier, I also need where did I start from to give you a better idea, and a region from Utica University to Syracuse University, so on. We'll get to those, but for now it's good to know that velocity is a vector. I have to tell a magnitude and a direction. For that, we have to symbolize a vector with a line, which is what we do. Let me draw actually a tilted line, show its direction and show its length. Then I'm symbolizing a vector nicely. So that's how we will symbolize vectors, and we already touched base on that as we are talking about motion diagrams, showing distances or displacements, which is also a vector. And how do we deal with them? First, we need to learn vector addition, and there are different methods for that. One is head to tail method. If I have vector A, like you see in this figure, and vector B, to add them using head to tail method, I take A, draw it without changing its length and direction. I can carry my vectors wherever I want. So I carry my vector to a position that is comfortable for me to draw it. And then I take my B and draw it as well, starting at the end of, or the tail of A, I believe. Draw my B, and then the addition, the vector addition, which is shown as R here, starts in the beginning of A and ends at the end of B. That's our addition vector. R, we call them often resultant vector, symbolizing that we use capital R, A plus B, but that's symbolically. Physically, A will be a value, B will be a value, physical value, and R, the resultant vector, will be symbolizing another physical value. We'll see it in lectures soon. But mathematically, or generally, we call this resultant vector. Oops. Did I mean to do that? I just need an eraser. Resultant. And that's it. The directions doesn't have to be like along a straight line like in the example we did. They could have different directions. Here I have A towards east, B towards north. I do the same. I draw my A, To guide your thinking, I'm gonna redraw these vectors. I draw my A. I can carry it anywhere I wish without changing its direction and magnitude. I start my B at the end of A, draw it, and my resultant vector starts from the starting of A and ends at the end of B, towards the end of B. That's the direction. Remember, a vector should be defined with direction and the magnitude. That's my R, that's my resultant vector. Notice here, A and B are along the same line. In the first one, I can just directly add them if I have a vector. Magnitude A, magnitude B, add them to find R. In the second one, I have them on a right angle. Right angle. We'll use this in forces a lot. We're going to add forces. And force is a vector. So if I know the value of A and B, those are, see my angle theta. I can use this to get to a value using trigonometry. And I can get to my R, magnitude of R. When I drop the arrow here, that means magnitude. We'll keep using this. Mostly we define the direction and then we drop the arrow for vector and use the magnitude. But if I am showing a letter with the arrow on the top, hat, that means it's a vector. If I drop it, that means I'm looking at the same vector, but I'm looking at its magnitude or the length of it. Alright, so I can also do that. So I'm going to drop the arrow here. I'm just going to calculate R's magnitude. If I know the value of A and value of B, I can use the Pythagorean to calculate my R. So Pythagorean theorem will keep coming up. And it will be hopefully an easy matter for us to calculate it as the time passes. So that's one type of vector addition. Another type we don't really use quite often, but sometimes the geometry allows it and we just go ahead and use it, is parallelogram method, this method here. In this case, we take one vector, draw it starting from a position, carry our vectors again without changing their length or direction is okay. So I carry my A here, draw it. Okay, I did my best here. I carry my B this time at the beginning of A. So I combine their beginnings, okay? And then I complete a parallelogram as shown in here. Complete a parallelogram. These dots are showing that. And I draw a diagonal to this parallelogram. And the end of my vector should be on the end of the diagonal. I start drawing from beginning of A and B. And I go down to the other side. That's the arrow. These arrows are representing that. That's my A plus B vector or resultant vector. Alright. The length of it and direction of it are like so. If a geometry allows it and it's easy, we'll use it. Quite often, head to tail or parallelogram method doesn't give us a good result. We're not sure what the answer is. We use components method. Components method is finding all the components and adding them. First, how to find the components of a vector. I have a vector here. I show my x and y coordinate system. X, as we reviewed in the previous lecture, is generally along east to west. This would be minus x if I show it here. And y is north-south. South is represented minus y. And north is represented by plus y. And I always, there are other ways, you might hear them here and there, but just listen to me in this course. Don't confuse yourself. We'll go the simplest way. We will always define the angle with x-axis, the smaller angle. In a bit, I'll tell you what I mean by the smaller angle. And then find the components using these equations here if we know that angle. Alright, this will give me the magnitude of the components. AX is a cosine theta, AY is a sine theta. And theta is the angle, the smaller angle, A makes with x-axis. What do I mean by smaller angle? There could be confusions that there's also this angle here. It's also with x-axis, right? Do I take that? No. Can you take that to solve? Yes, but I don't want you folks to worry about that. We'll only go with the smaller angle. And the direction of these components I will define by drawing lines to x and y axis, where they hit the axis at a 90-degree angle. I'm going to draw a vector to there from the origin. This would be my origin here, 0x, 0y. And I draw my components to the point where my dashed lines here hits the x-axis at 90-degree angle. That's my ax, and that's its direction. Now, as I see here, is to the right, to east, and I'm going to say my ax is positive. It's a vector. The direction is important. And the same goes for y. I will draw dashed lines and find where they hit y axis at a perpendicular angle. Then I'm going to draw a vector starting from origin to that point where my dashed lines hits the y-axis. That's my AY. Guess what? My AY is also positive. It's upward, north, and we are symbolizing north or upward as positive. If I know by AX and AY by any chance, and there will be chances like that, there will be situations we know AX and AY, how do I find A? If you look at this here, you guys see a parallelogram completed. You guys see AX and AY are starting at the same point. They are added together, and diagonal is A, right? I can also imagine, and I hope you guys can also imagine, that I can carry this AY from here to there. Let me actually try to carry it. I can take it and carry it here without changing its length, right? And it will be the same AY. So I can complete a triangle here, this yellow side and the blue side. And I will have a right triangle that I can use to find my A. Use Pythagorean. So I can always use Pythagorean to find the total vector if I know its components. So A here will be x squared plus AY squared. And the direction is like it's seen in here. I can also find angle theta using trigonometry. How do I do that? I can use tangent, sine, cosine, depending on what I know. But if I know the components, tangent, opposite, or adjacent, right? Theta is equal to tangent 2 minus 1, opposite, AY, this guy over here, or adjacent, AX. So we will also always use tangent to get to the angle. Other ways, of course, possible, cosine, sine, but often it's easier to find the components and go tangent. It's also easier for you folks to settle down and be comfortable with one certain approach that we're using, and we will be using that, tangent. This question here is about a distance displacement. This is a vector. So we're already solving a physics question here. They call it R. I'll leave it as R. 175 meters as shown in the figure. That's how the direction shown in the figure. That would be my X. That would be my Y. And the question tells us what is the X and Y components. I'm going to call them Rx and Ry. They call them X and Y. Let's drop that. I'm going to show them as vectors, but we know their directions, right? X is along positive X. If I have my R again, let's go over this. Drawing dashed lines, right, where they hit the x-axis, and then drawing a line, vector line from 0 to that position. That's my Rx, and that's its direction. As we see here, folks, Rx is positive, right? This is positive X. Do the same for Y. Draw my dashed lines, right? Where they hit the y-axis, I draw a vector starting from origin to that point. That's my Ry. And guess what? Ry is also positive. Direction is up positive. Direction is right positive. What they did here is to carry. This should be Ry. Don't get confused there. My Y is not looking good. Let me rewrite this, dude. Alright, Ry. They carried this Ry here already. So I can carry my vector without changing it. Remember, I'm going to draw it here. It's the same. It's exactly same size, same direction, only not starting at the same point, and it's always okay to carry my vector to position that will make me more comfortable to calculate values. That's what they did here. And this is a simple question actually. We have Rx is equal to R cosine 50. That would be our angle, theta, angle with the x-axis, remember. That would be 175 meters times cosine 50. Once you put these into calculators and multiply them, you should get an answer of, quickly find my number here, 112.49. meters. Direction, positive. Ry, R sine, R times sine 50, 175 meters times sine 50. And that will give us a value of 134.06 meters. And that's it. That's it. If I am adding two vectors here, notice that I have head to tail method. Head to tail. I have A here, right? I carried B at the end of it, right? And C is starting from the starting of A, going to the end of B, towards the end of B. That's my C. And it's equal to A plus B. But I'm not sure how long this vector is, if I want to know that, or what angle it makes with the x-axis. If I want to know that, I want to go component method. What we do with component method is we find the component of A, x component of A, x component of PB, and add them. Careful here though, we add them as vectors. Sometimes they're not in the same direction. They're in the same direction here, we're good. And then we draw component of y component of AY and y component of BY y component of B, and add them, then we have a better understanding of what C is. C equals A plus B. Notice this is vector addition. Doesn't mean necessarily I just add A and B. No. What I do is this. I say CX vector will be AX vector plus BX vector. Sometimes one will be negative. I'm going to add that, so I'm not dropping these heads yet. They are vector additions. And then CY vector is AY plus BY. I find those, and then I draw my C vectors, like in the third picture here. I'm done with A and B now. I added them. Now I have my CX, and I have my CY, right? Then I use Pythagorean to find C. This is my angle theta. I want you folks also imagine here, which will be useful, an X and Y coordinate system. I should have chosen maybe a thinner line here. So I'm assuming I have Y here, and I have X, right? That's assumed but not shown. And so on. Then I can find my C. After knowing CX and CY, I can find my C using Pythagorean. Because look here, I have a right triangle, and I can use Pythagorean to find C. CX squared plus CY squared. Magnitudes. Direction, I see it here. Let me redraw my C. I see the direction here. It makes the angle theta with x-axis, positive x-axis, I can say that. But to be more clear, I want to calculate that angle maybe. And I can calculate that angle. Plus x here, plus y. How? Using tangent to minus 1. cy or cx. Always y over x. And remember, that's the angle with smaller angle my vector C makes with the x-axis. Now I'm hoping this question here will take some time to solve, but it will help you folks get on board with very hard solutions for adding vectors and components. Main idea is I'm going to find all the components, define them as positive or negative, add x's, add y's, and find the total using as the same method as we used in the previous question. So let's see what we have here. We have three displacement vectors, A, B, C. A is 5 meters. Notice I'm drawing my picture here, but they mostly draw it for me. B is 5 meters. And that's how they are directed as shown in figure, and C is 4 meters. Find the resultant magnitude and directional angle. We'll find the angle it makes at x-axis of the three vectors by means of components. First of all, I want to show the components to see if they are positive or negative here. Draw my lines. The x and y axes. Where they hit the axes, I draw my arrows from the origin to there. Draw my arrows from the origin to there. Find my components. Now the first ones I draw is B, x and by. And I look at their directions. By is upward, so it's positive. Whatever number I'm going to find, it will be positive. Bx is up to the right, it's positive as well. Do the same for A. I'm going to use yellow here. Let's use a thicker lines. Draw a line to X and Y where they hit X and Y. At 90 degree, I draw my components. Didn't work well. Go back and redo this. Alright, a bit longer than it should be. Let's try again. Alright, this one is good. This is my AY. From the origin to where it hits x-axis, this is my AX. I'm gonna write them, and I see that AX is to the left, so I'm gonna mark it as negative. It's a negative value. Left is negative, right? And AY is up, same as B, so that's positive. For C, it doesn't have any X component. It's totally along Y. And its Y component would be just itself. That's all. This is a simple matter. This simply C is equal to CY. And CX is 0. Alright? Now I'm going to list all the components, all X components. I have AX. It's A cosine 20. You see the angle there? And that value, should have that somewhere, should be 4.69. I have units as meters, so I'll just put units there, and I decided that it's negative. BX. B cosine, the angle B makes with the x-axis, 60. And it's 5 times 60 degree, cosine 60, sorry, B cosine 60. And that value is 2.5 meters. And I decided that's positive. And I decided that C is only along Y, CX is 0 meters. Now, let me symbolically define the total, let's call it R, we often call it R, resultant A plus B plus C. This is vectorial addition, so I'm going to give my hats here. And I know that I'm going to add these to find Rx. That is also a vector, right? Let's actually write it down here. It will not fit in there. I'm going to erase this dude here. So I'll say from here Rx, vector addition, I don't know its direction yet, but the answer will give it to me, is equal to AX as a vector, so direction matters, plus or minus, BX plus CX. And when I put the values, I have to take this dude as minus, negative, so it's negative 4.69. Now I can drop the vector and put it in values, and I'm adding the direction with plus and minus. Alright, BX is 2.5 meters, CX is 0. I'm going to find from here, I'm going to check my answers here, minus 2.19 meters. Similarly, I find all the Y components, list them. AY will be A sine 20, and that will give me a value of 1.75 meters. That's positive, I decided already. BY, B sine 60. When I put in the value, that will give me a value of 4.33 meters. and this is also positive, and cy, which I forgot to mention, is downward and negative. It's equal to c, simply minus 4. Let's not do that, put the minus later. 4 meters down. You can also put it as minus 4, doesn't matter. Then what we do is we add all those, mind the directions, right? So ry is addition of ay, by, and cy, and I put in all the values. With the signs, I'll get a value of 2.04, positive. All right. Now, if I show these symbolically, let's add a new page actually. Here's what I found. I found that Rx is equal to minus 2.19 meters, right? And Ry is equal to 2.04. First of all, I know this blindly. I can find its magnitude because I know it will be from Pythagorean when I draw them and complete the angle Rx squared plus Ry squared. I can find the magnitude from here, but that would be quite blindly 2.99 meters per, not meters per second, meters. I won't know the direction and so on this way though. What I want to do to get a nicer understanding is to draw an XY system. So this is plus X, this is plus Y, and the other side's minus and so on, right? And draw my vector components, Rx and Ry. My Rx is negative, means it starts from the origin and it goes to the left. And my Ry is positive. So it starts from Y, goes upward. Lengths are close to each other, so overall I'm drawing them close to each other. It doesn't have to be perfectly correct here. And okay, let's carry this a little bit to right. So these are Rx and Ry, positive Ry and negative Rx. Then what do I do is I complete this to a parallelogram, which is in this case simply a rectangle. And I draw the diagonal vector, and that's my R. Now I have a better understanding of how R looks, right? It's towards leftish, upward. If I use north, east, west, north, south, right? I would say it's northwest. With an angle, I don't know. Theta, small angle with the x-axis. Remember, not this angle. Not this one. Let me delete that. The smaller angle. And here's its magnitude. I already calculated it. Now I know its direction too. Kind of know. I know overall how it looks, but how much away from the x-axis, negative x-axis, right? Let me rewrite this as well. Oh, I wish I had a better handwriting. Alright, slowly. Write it nicely. This is minus x. Then I use black here. Okay, a bit better. Now we're going to find theta. We already know from before that we can find theta using tangent to minus 1 Ry over Rx. So I'm going to punch in tangent to minus 1 in my calculator, and over here I'm going to put Ry 2.04 and 2.19 Rx. That should give me an angle of about 42.96, about 43 degrees. Now, if I think about the logic of this, if it makes sense. It makes sense because I have 2 and 2 different, slightly different from each other. The result should be slightly larger, but still close to 2, 3. It's good. And the angle equal sides, I know, should be close to 45. It looks good too. All right. This is the hardest part, my friends. If you are getting some of this or most of this, is very good. Vectors are our main, your, not mine, main concern in this course. Vector subtraction is simply vector addition. So I'm not going to spend too much time in here. We'll also do some examples in class. Vector addition head to tail. What we do is we take A, add B at the end, and the resultant vector is from the beginning of A to end of B. If I want to do A minus B, I take A or C minus B as it's shown in this here. I take C as the same. Then I inverse B, that would be minus B. But the minus B should be parallel to B. Same length, or anti-parallel would be a better option here. Opposite direction. I carry minus B there. Simply then still do head to tail. Simply beginning of C to end of minus B is C minus B. My vector, A vector, which is equal to C minus B. The same goes for components methods. We'll look at a components method 1 in class. Now I'm going to quickly tell how this is related. 1. Displacement. How much I move from my original position to final position called displacement. It's a vector. I have to say direction so people know from where to where I lived. I moved 100 meters, but from where to where I went, right? I went from school to home, then it gives a sense of direction. Generally, we have it in our speech. We assume it, we understand it, but we don't think it should be giving me a sense of direction. It should be a vector. Now you guys are starting to think about that, right? That's why physics makes you wiser. All right, we should give a directional sense to say how our position changed. That's a vector. That's called displacement. Change in position is called displacement. It's a vector. We always find it using the final position minus initial position. And the result tells us if it's into east, west, or plus x minus x. If I have plus 100 feet in this setup I have here, I'm setting my x along 12th Street, right? So I know what I'm talking about. I'm taking origin 0 to be Wine Street and 12th Street, so I have my x line along the 12th Street. Let me actually draw it here. This is my, oh, I actually draw it here. Let me draw it down here. So this is my X line, right? I'll pull this a little bit up. If I was going to left, it would be negative, but I'm going to right is positive. I move from 50 to 150. I moved 100 meters to the right. Time is a scalar. 1 second, 2 seconds, 6 seconds. I don't have to define a direction. This is an example, a very simple example, but it nicely summarizes the problem-solving approach we will use. This is how they are described in the book. So let's read the question first. Emily is enjoying a bicycle ride on a country road that runs east-west past the water tower. Define a coordinate system so that increase in x means moving east. At noon, Emily is 3 miles east of the water tower. A half an hour later, she is 2 miles west of the water tower. What is her displacement during that half an hour? So first thing is strategize. Think about what is happening, and what you're going to be using, we're going to be using particle model. Again, I personally like drawing a picture of Emily walking from here to there. Put a dot in the center of her or here, just to imagine it better. And then she comes here. Particle model is also good. Initial position, x initial. Final position, x final. Think about what you're going to do. You're going to draw a picture and prepare for solving the problem. That's very important. I call this part drawing an ugly picture. Then you look at x initial, x final, and you find your delta x. It will be minus 5 miles. You move it from +3 to -2. And if you look at your picture, you can easily see why it is minus. Emily is moving towards left or west, so it should be minus. When I put in my numbers appropriately, final is -2 miles, initial is 3 miles, it also gives me that. So it makes sense. I solved it correctly. So if I solve and I find this answer, I go back to my picture and think about what would that represent, if it makes sense. That's what we call assess. Always think about, did I do this right? So these steps will always be in the book. We'll go back to them on and off, but keep them in mind, even if we don't mention them. First, you strategize. Think about what you're gonna do. What is this about? It's about emotion. Then draw a picture to prepare your mind. Here it will come also to write down and show what you know, what is given, and think about what is asked, right? I would say here, I'm gonna look for the value of displacement. This guy is a vector. I have to show direction too. Here I'm looking at its magnitude when I drop that vector. All right. Then you solve it. Apply the equations, you know, and then you think about if it makes sense. So assess it. That will always be our problem-solving strategy. One more thing about displacement is that it's independent of the path. Okay, it's equal to final minus initial. It's a vector subtraction. We have to be careful about. If I'm going from A to B, no matter what path I take, path 1, path 2, path 3, doesn't matter, my displacement is always the distance between initial position to final position, and its direction is toward my final position. Of course, I'm going from A to B, direction is from A to B. That's logically understandable. All right. Jane and Sam might be moving same displacement, but depending on the directions they move, where they will go will change, right? It won't be the same. This picture here nicely showing how the displacement is depending on distance between initial to final position. A, straightforward. B, straightforward. Right, we moved on a straight line. But C curves around. Displacement is still between initial to final position. D is curving around. Displacement is that. So we will always look at the distance between initial to final position, and the direction of displacement is towards the final position. Logically, it should be. That's where I am going, right? And this is all delta x values. It's a vector, my friends. This one is just asking graphically, so I'll quickly draw. Jen runs 1 mile north, east, and then 1 mile south. Overall, show her displacement, x or east, right, west, will be minus x. North will be y, and south minus y. She is going northeast. When we say northeast, we assume it's like a 45-degree angle, 1 mile. Then she moves south 1 mile. This would be the south. Would be somewhere here. So 1 mile northeast. Oops. One mile south, and her displacement would be overall this guy over here. Logically, right? That's her delta x. Alright, my friends, I'm going to cut this lecture here and we'll look at some examples in classroom.